Okay. Well, you said 20 seconds, right? Five, four,
It's okay.
three,
I'll give you three
two,
extra seconds.
1. Okay. Thank you for the presentation, and obviously let me thank the organizer for this very nice meeting and to give me the possibility to speak about this new approach to BFKL limit. And this is an ongoing project. Will be out soon, hopefully, with Simon. Simon today was advertised 3 times, so is the his day apparently. And Kolya. This new approach, we call it ABBA. And obviously, if you think about ABBA, first off is ABBA, so the most well-known disco band ever. And as you can see, like ChatGPT is kind of sexist because the female part of ABBA is not here. So apparently only male members. But what they are doing, they are obviously discussing about physics. And which kind of physics? A lot of different topics, no? Like similar stuff that Istvan was talking about. So conformal regge theory, n equal for super mills, QCD, and maybe maximal transcendentality connecting them, integrability, obviously, BFKL, DGLAP, light ray, hadron scattering, horizontal trajectories, and so on. So all this blah, 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 blah by them can be recasted in this acronym, and this acronym means asymptotic Bethe Baxter ansatz. And what I'm trying to do is to explain actually what this new approach actually means. Okay? So since Istvan was doing the seminar before me, I'm obviously using all the definitions that he gave you. He did a very nice history about BFKL and horizontal trajectories, etc. But just to remind you, since there was the coffee break in the middle, this is the vocabulary of regge trajectory. We have this kind of Fauci plot, that is a plot of the spin in terms of the dimension. And we have two regimes, DGLAP, so the pointer is working, DGLAP, that means the diagonal trajectory, and BFKL, this flat horizontal one, okay? So in DGLAP, what is interesting there? It's interesting because local operators of the twist that we are choosing, they are actually sitting on top of the trajectories there. And for example, you see BPS operator is here because for different values of G, all the trajectories are passing through here, okay? When G is equal to 0, the trajectory is the black one. So it's actually a collection of straight lines, if you want, that they are meeting in a point here. And when G is not 0, they start to bend because there is some kind of mixing between this trajectory and something else that we will see later. That is going on, obviously, when G is not equal to 0. Cool. So when we have physical operator, usually we always talk also about shadow operator. There is a shadow transform, that in this case means shifting delta to minus delta. Okay, so we have another collection of operators there. They are the shadow partner of the operators in the right-hand side. Cool. Then, BFKL regime is a totally different kind of regime. It's this flat area that sit on top of the horizontal trajectory. So the whole horizontal trajectory actually can be approximated in a BFKL-ish way. And what is BFKL? Istvan was speaking nicely about this stuff, all the history about this, but like very briefly, was found that some integrable effective Lagrangian was describing QCD in this regime. And then the same could be done for the SL2 spin chain that is connecting all of this discussion to n equal 4 super mills. So we can study n equal 4 super mills, these objects here. And just to give you a nice picture, like an old picture, like Simon was saying that this picture, actually we don't have to use it, but let me use it for a moment. Last week, I mean. Actually, the picture is you have some kind of rigid gluons, some very heavy gluons, and in the middle you are resumming an infinite set of ranks. Any rank has a kernel that you have to resum like a beta salpeter, and any of them, this kernel has an eigenvalue that is equal to this object here. So this is a very well-known, very famous formula. This is the eigenvalue of Pomeron. Psi is a polygamma function, psi 0, and gamma is the Euler gamma, okay? Cool. And this is appearing everywhere in physics, in particular in BFKL, QCD, etc. Cool. Last few remarks about these pictures. Those red points are branch points. Indeed, you see the black line are meeting there, and then the mixing actually is happening around it. But there are many others on the horizontal trajectory. There is an infinite amount of them, okay? And then last stuff is that what is encoding BFKL is encoding also if this is working, maybe not. At some point it will work. Not now. Not even now. Okay, it's not working anymore. Again. No. Ah, now it's working. I guess so. I have to point there, no? Okay, now it's kind of working. Not anymore. Do you have any idea what is the sensor? I tried, but it's not really changing anything. Thank you.
You can click here to pass the slide again, and the animation will go.
Okay. Thank you. Okay, we were here. So let me start where we were. So, like Istvan was saying, there is a very special point on the horizontal trajectory that is the intercept point. So when S is computed for delta equal to 0, and this is very important point because the intercept actually is give you insight of how the 4-point function is actually scaling. And in general, for example, in QCD is telling you how some scattering is behaving for high energy. Okay, and this is the observable that usually we like to compute when we talk about Regge trajectories. Okay, cool. So how we compute Regge trajectories in n equal 4? We use the quantum spectral curve, but let me say, quantum spectral curve is actually working for NEG is non-perturbative, but those two different behaviors, like DGLAP and BFKL, are very different. Indeed, DGLAP that contains a local operator can be described by asymptotic Bethe ansatz and is a perturbative kind of expansion, and is okay up to wrapping. But in the BFKL regime, is totally non-perturbative. So how we can connect them? And QSC is QSC is able to the connection between the two because it's non-perturbative. We can continue for NEG, so we can go very IG, for example, and we can interpolate between the two regimes, okay? And just to give you pass the message of what quantum spectral curve is, imagine that is a big box. You want to input something and having some output. The input are some quantum number, those are the same quantum number that Istvan was showing. The Cartan G1, G2, G3, the scaling dimension, spin, conformal spin. You put it in the box, shake in the box, and then at the end you have the spectrum, or in our case, that is even more important, S as a function of delta, so the other way around. So quantum spectral curve knows about the analytic continuation, okay, automatically. That's pretty cool. Indeed, if we are opening the box, we have the QQ relations that you saw many times also today. And what is important of the QQ relation, that the asymptotics of those Q functions contains information about the quantum numbers. Then we have analytic properties, so we have to understand how those P and Q actually pass through cuts and they merge, let's say. And what is interesting here is that cuts encoded the presence of the coupling. So there is no coupling here, but there is coupling here. And so putting it together, we can solve, let's say, delta for some value of G, and G is telling you how big is the cut, okay? And then last stuff that is peculiar for the BFKL, for example, let's say Regge trajectories in general, is that we have a gluing matrix that is pretty different respect to the standard one for operators. So it's not constant anymore, but contains exponentials that contains U. And so it's a bit more complicated, okay? So, an example, we can put inside the box SL2 sector quantum numbers, so these kind of operators that are very under control. So S is the spin, L is the twist of the operator we are considering. Shaking the box, and we have some data, for example, delta of S, when S is equal to 2 and L is equal to 2, this is the Konishi, that is interpolating perturbation theory and string theory. Okay? Cool. This is the picture of what is quantum spectral curve. But then the box actually exists, and if you want, the last time I saw this box was in KCL in some room. So if you want to go and discover some secret, go and I'm pretty sure it's still there. Okay. Anyway, let's go. So quantum spectral curve can compute delta of S, but when also delta and S are actually complex. So we can actually explore not only real plane, but we can explore the entire Riemann surface. So we can really understanding how the branching for those rigid trajectories are actually working. For example, L equal 2, this is the Pomeroy case. We have two sheets, and they are behaving in this way, and there are some branch cuts here. They are connecting the two branches. For L equal to 3, this is what Istvan was showing. It's way more complicated because you have more degeneracy. You have three sheets, they are connecting, red dots are branch points, and you see that G is pretty high, let's say, and branch points are sitting here in the imaginary side, imaginary part, let's say, of delta. So they are sitting far from the real plane. These are standard feature in this stuff. And then when G is going smaller and smaller, the branch points are going back to the real plane. Okay? Cool. But we can do something more. Can you click the picture, please? Hello? Okay. So we can go to twist4, and there are more branches. Those are just few of them, and you see that we are moving in the imaginary of delta. And so you see that some branching is starting, many planes are connecting each other, and it's way more complicated. So what is going on? So when we raise the twist, how many Riemann sheets are connecting each other? Which one is connecting with which? You know, like this is pretty weird with respect to the one before. Like doing twist 4 is way more complicated than doing twist 2 and twist 3, and we don't have any clue how to understand this stuff. For example, even a weak coupling. Okay, this is another vision of the same picture, and you see all these branching here that is connecting not two but sometimes more sheets and so on. And if you cut in the real plane, you see the standard trajectories. So the one that I was showing in the first slide, like the Cho-Frauchi standard plot. Okay, this for G equal to 1/2, so it's pretty big. So let me cut it in half, the cake, and reduce G. So if G is equal to 0.1, you see that the trajectories are going closer and closer. And this is what actually we expect, looking at what Istvan was saying, for example, for twist 3. What is happening here? This is a bit more, crowded, this area here, respect to twist 3. Why? Because indeed, twist 4, let's say, is the first twist in which we start to see some very complicated feature of rigid trajectories. For example, let's do a counting. First operator that is appearing is the BPS1. Fine. Second operator is appearing in the blue trajectory, but there is another one in the orange one. So there are two operators for spin 2. But then there are three operators for twist 4. Then there are four operators for twist 6. So for spin 6. Sorry, I had to say spin. But I mean, this is continuing and there is a pattern. And so there are infinite lines that are passing through. But what is the cool stuff that actually is happening also in all the lower trajectories? So if you're going here, for example, those are twist 6 operator. There are just two. Okay, cool. Only two? No, they are 2 over on 10. So there are 8 missing there. And then the counting is continuing and growing like crazy. So what is going on? It's going on that, for example, the red line, the red twist, the red trajectory, for example, follow it, is going down. It's actually not bending here. It's going down and bending at the tip. So it looks like that some of the trajectories are bending like we are expecting on the horizontal trajectory, and some of them, they are not. Okay, cool. Maybe it's a bit more clear when G is even smaller. And you see that, indeed, just 4 trajectories are appearing in the horizontal trajectory here and there. And this is continuing. The same pattern that this one was showing for twist 3, that we have 2, and was a repeated pattern for all the horizontal trajectory. Same stuff here. This is a repeated pattern for all the horizontal trajectory, but this time we have 4. And where all the other infinity are going, infinite number of trajectories are going, you see again the red one. This is a magnification of this branching point, and the red one doesn't see the branch cut, it's passing through, and then resolving here if you want. And so we expect that we have an infinite amount of them that are doing the same stuff. So the point here is that few trajectories are bending, infinite amount of trajectories are non-bending in general, and the one that are bending, for example here, they are the leading one. Cool. So obviously we want to learn also about the intercept, okay? So we compute S for delta equal to 0. Obviously what I'm talking about here is just numerics. So this is a brute force, but I mean like we have a very, very, very efficient code that is computing point by point this curve, and then after a super long time, like thousands of points, you can build all those curves, okay? And to go to the intercept, you just go very close to 0 and then continue in G, because we want to know the intercept as a function of the coupling, okay? We go in this point, and what is happening? We have 4 trajectories, so we expect 4 intercepts. So this paper is very ongoing, so I just have data for 2, so I'm showing just 2 of them. But what we see here, okay, 2 curves that are interpolating between -3 and some value at large coupling. But the point is that we have no clue how we coupling, how to treat them, because we have no analytical data. But what we can say is that interpolating the weak coupling behavior, we can see that the blue trajectory behaves like G. Remember what Isfan was showing, that this kind of weird linear behavior in G is appearing again here. But also there is the subleading trajectory, the orange one, is going as G square. So it looks like that for twist 3 we had just linear terms, let's say intercept, and in this case we have both. Okay, this is curious. So let me put everything together. We have twist 2, 3, and 4. We have numerical data that we know, and we can analyze and decide what to search for. We know the degeneracy because we measure it with numerics. So we know that there is just one horizontal trajectory for the Pomeron. There are degeneracy 2 for twist 3 and 4 for twist 4. Okay. Then we have intercept data. Some of them have a very nice interpolation. This one just the linear term. For twist 4 we don't know anything. And for example, we can reproduce the leading term for Pomeron, and this is very well known in the literature. That's fine. I'm not very spending time on it. But analytically, for example, here for twist 3, we just know the leading term. We just know how to fix plus minus 2 from the Isfan talk. Okay. Then delta equal to 0. This is the intercept. You just put delta equal to 0 here. And you have this object here. And you see this is independent on delta, interestingly, for some reason. We'll see why later. But we don't know anything else. So all the rest, we have no clue analytically how to compute or understanding what is going on. Okay? So this is the whole point about this ABBA description. Because which is the philosophy of this new description of BFKL of weak coupling. The point is that we know quantum spectral curve that is working nicely and non-perturbatively. But sometimes, one is interested to go, for example, to the local operator point. We can put G very small and L pretty big, and we are reducing QSC to be the standard asymptotic Bethe ansatz. So there is a way to do some similar kind of limit in the non-perturbative side of the Cho-Frauchi plot, so in BFKL. So this is the point. And the philosophy is indeed, you look at how Q functions are gluing on the cut. They are doing it through a tensor that is omega ij. So omega ij is the monodromy of these Q functions. Those Q functions have some precise scaling, and we can study the scaling of this omega. And depending on the scaling of the omega, we can reduce QSC to be simpler. And then we study the zeros of mu AB. So let's say mu AB is the monodromy of P, but then mu12 is encoding a lot of information, and in particular zeros of mu12 are related with these momentum carrying roots. And then we can associate them to magnons and compute the dispersion relation, the energy. This is the standard strategy. That for ABA, for asymptotic Bethe ansatz, is the well-known one. So the dominant term is omega 12. We compute the zeros in the strip, and we plug everything in the formula, and we have the standard dispersion relation. But for the ABBA, this new description, the dominant is omega 13. And this is changing everything, because we have 4 new roots on the cut of mu, that we can parameterize in this way, plug inside the dispersion relation formula, and we have a different, a new dispersion relation for S of delta. This S of delta plus L minus 1 is playing the role of energy, okay? And is actually the horizontal trajectory, so this is the horizontal trajectory. And you see, this is pretty curious, because if you sum this stuff, looks like a massless the dispersion relation that is similar to what is appearing in the GS3. This is pretty curious, okay? Say it again? I've done this. Yeah. So let me be a little bit more precise. So this simplification of the QSC means that just few of these 256 possible Q function are playing a big role, and are those 4 here. And interesting, some of them can be written in terms of the new roots and a new dressing phase that contains also the roots. But anyway. And then one of them is pretty interesting because one of them cannot be written in a polynomial term, but is just a solution of a Baxter equation. But this Baxter equation is actually the whole loop generalization of the famous Lipato of BFKL1. So when you are putting theta are actually the Zukowski variable version of the new roots. Okay? When you're putting theta to 0, you are going back to the Lipatov stuff. And an interesting stuff is also that this in principle looks kind of hard to solve it, but at the end it's not that bad. Indeed, it can be solved exactly in terms of a 3F2. And this may be one of the motivation why BFKL is that simple in some sense in this configuration. Okay? Cool. Then having all those information, one can study gluing, and when you study gluing, you remember the gluing condition for analytically continued trajectory is not just a number, it contains u, there are exponential, and so there is a long derivation to do it, but studying this gluing condition between Q1 and Q3 and relating with Q11 and all the other cool Q function, we can fix the number of solution to B4, like we expected, and we can also write this nice formula. This is a ABBA kind of formula, where you see, as appearing the dressing phase, some combination, the collection actually of all the roots, and this G is some bunch of gamma function that contains delta and the thetas, okay? So this is pretty ugly, but just as an example, we can just go brutally at G equal to 0, like a G very small, and what is happening here? The dressing phase is 1, and all the thetas are going to 0. So simple like that, like all the ABBA relation is just 1 equal to I zeta to some power. We have 4 of these equations, and we solve them. So the solution is just the roots of the unity that is parameterized by this integer nk. So nk can have some values between 1 and L plus 1. But then we also know from this system that 2 of the solutions are related. So instead of computing 4, we just can compute 2. So we reduce the number of solutions even more, but plus, still also from the previous equation, we have another condition that is actually a selection rule that is telling that N1 and N2, they have to have the same parity. And so we can put all this information inside the dispersion relation, and that's it. And we have the full solution at order G. Okay. This is cool, but in principle, zeta k can be expanded more. So I can add some, can do an ansatz with a term G, then G squared, and blah, 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 and put it inside, expand it again, the big ABBA equations, being a little bit more careful, and I can have another term, and so on, and so on, and so on. Okay? I'm putting here just the first 2, and some interesting comments are, 1, look at the first term. This is independent of delta for any L. So what we were seeing before, this plus 2 minus plus minus 2G, that we were noticing that was independent on L, is actually a true statement for any L. And then chi of delta, so the whole dependence of delta, at least up to G cube here, for example, you see that the whole dependence of delta is actually encoded in the Pomeron eigenvalue. Interesting stuff too. And then, since is a asymptotic kind of computation, obviously we cannot push forever. At some point we have to stop, and we have to stop at G to the power L plus 2. So the last cool term is G L plus 1. From G L plus 2 we have some kind of wrapping-like terms that we don't know how to compute. Okay? So let me just show this stuff in action. So we have this is the solution. We have the maximal values that n can take, and the selection rule. So what we can do? We can start to count. So twist 2. And k can go max to 3. You have 1, 2, and 3, and the other side 1 are N3 and N4. Remember, we are just checking N1 and N2 because we have this relation that is connecting them. So let's considering only the right hand one. So since n1 and n2 they have to be even, there is only one possibility. So n1 has to be 1, n2 has to be 3. That's it. So this means that we have only one possibility, and this is exactly what? This is the degeneracy of the trajectories on top of the horizontal trajectory that we were saying before. You repeat for 3, and indeed you find 2. You repeat for 4, and you find 4. And then you can continue, and this is the general formula. So we know now, for any twist, how many trajectories are sitting on top of the horizontal trajectory, okay? And we can play another game that take the formula before, just the leading order, the G term, and then we can plug n1 and n2 inside. What is happening here? We plug n1 equal to 1 and 2 equal to 3, we plug it inside, and what is happening? That this will be equal to 4g cosine of something minus cosine of the same stuff. So it's automatically dropping down the G term. So the G term is dropped. So for this configuration, we have no G term, just G square, as expected. Twist 3, this is not happening. So the cosine, they have a plus. And so we have two solutions, plus 2G, the one that Istvan was showing, plus correction in G square. And then you repeat. Twist 4, you see this strange behavior, let's say, kind of strange behavior that we were seeing from numerics. Two trajectories have linear terms, two trajectories have G square terms, and so on. And you can continue up to the time, up to the L you want. Okay? So now we understand degeneracy of horizontal trajectories and how to plug those numbers inside the formula and having our result, up to G to the power L plus 1. So let me do some, I'm flashing you some result. So L equal to 2. We have the, just to remember you, the Riemann surface is looking like this. We have one trajectory on the horizontal trajectory, and this is the solution, up to G square. This was known, nothing new. Fine, we check it, and it's working. Twist 3, two trajectories, that they are related by G going to minus G, like we were noticing from numerics with Istvan. So those two trajectories are related. This is the term that we knew before, and then some new terms up to G to the 4. And then twist 4, again, two trajectories related to G to the minus G with the odd powers of G, and then two trajectories with just even powers of G. And everything looks fine because we match the degeneracy counting that we had. The green one, we match the known analytical computation of before. The red one, we can match it easily with numerics at very high precision, and then we have all the black stuff that is just new. And then we can continue, L equal 4, L equal 5, 6, 7, 8, 2,000, 3 million. That's it, and it's very efficient. Then, obviously, we want to compute also the intercept. We have data for the intercept. Let me repeat this stuff. Intercept L equal to 2, fine, we know a lot of it. This is known, we check it, fine. Twist 3. So before we just add interpolation with the linear term, but now we can interpolate more, and you see, obviously the line is approaching, approximating better and better. Same stuff for L equal 4. Before we didn't have anything to compare, and now we can compare, and you see the two check with the dotted line that is actually the analytical part, is fine. Blue is blue, obviously, orange is orange, I guess it's clear. Unfortunately, I don't have data for the black one, but has to work also for this one, I hope. Anyway, so this was just...
In principle, you are out of time. Now it should be questions, but if you have one more minute, that's okay.
Sure, it's just 1 minute, just to show, flashing this slide. I wanted just to flash this stuff. That is, we can also try to understand if we can go from BFKL to the GLAP and reshuffling the variables in some way, re-expanding close to the branch point. You just can reproduce, can build, let's say, a third order equation. Third order because we know that 3 trajectories are actually interacting there. And then we can plot it, and looks like this. And you can do the same stuff for L equal 4, so these are matching some previous result, but you can do the same stuff for L equal 4. And this is not unexpected, because indeed, Istvan showed you this stuff. This is pure numerical prediction, and this is just the analytical computation. Same stuff for L equal 4, and you see they are matching, they are exactly the same. And now just, okay, just to shock you, but I can skip it. Maybe if you're interested, you can ask a question about it, and then I just flash the open question that we have. Thanks.
Thank you. Maybe, okay.
Is it clear which scattering theory leads to this ABBA?
No, this is, I guess, very related to the first point there, no? That we have no clue about this kind of interpretation, what is actually the correspondent field theory object. And could be nice to understand it. I mean, like Simon last week was talking about this dipole evolution, like ray operators, quadrupole, and so on. Like, could be very interesting to understand in this sense, but we still are trying to understand it, so we don't know.
So you had 4 beta roots, right? This
yeah.
Why 4?
But it's related with the shape of the gluing matrix. So it's related with the fact that you have exponential. There is this. So let's say if you want to be very deep in computation, there is at some point some condition that you have to respect to solve the system, and one of them is related with mu and mu with 2 pluses.
But my question was about the physics. Do you understand what these are physically?
No, okay. If you tell me, if you ask me, like if there is a physical intuition to say why 4, no, I don't know.
Volodya has a question. Can you get the phone back 2 rows, please? No, not the phone, the microphone. You have to turn it on, I think. Click the button for 1 second. Yeah, you press the button for...
It's the same.
You press it for 1 second.
Okay, yes. I figured it out. So you have the V-coupling behavior for many of these operators like G and not G square, which means that you resum the graphs and you have some square root singularity. So I want to understand what it means for Feynman graphs. For example, for the standard dispersion relation, we know how to sum up the ladders like Reuben, Gross, and who else I forgot. But here, what can you say about perturbation theory? Because if you start from G, it's not really a perturbative result.
Yeah, I agree. In the sense, like, obviously we have the habit to see local operators with quantum spectral curve and integrability in general, and everything looks fine. Like everything is a power of G square, and we are very happy. Indeed, he's very curious about this kind of behavior as G of some trajectories. But the point is that, like, speaking also with Simon last week, looks like that this kind of behavior could be like in their picture, like a field theory picture, like ray operator picture, is just probably some result from some weird mixing matrix that has, for example, a diagonal to 0 and then some anti-diagonal object that is depending on G. You diagonalize this object and you have some condition like G square equal to blah blah blah, and then you take the square root, some kind of square root behavior of the mixing matrix. I guess I would guess this is the answer, but I don't know, because we don't have a clear approach in Feynman diagram sense.
So another way to say, well, so you normally used to say that BFKL is resumming the single log G square over omega contribution, but this setup, when you have linear terms, it means that you are resumming more general double logs divergences, which are the form G square over omega square. And that's indeed what people found up to for loop by studying in this paper of Lipata, for example, Staudacher, Ray, which, yeah, this one. So it agrees perfectly with this, because you see this last line is a resummation of G square over omega square rather than G square over omega as you used to have.
I see. Thank you.
Well, there are no more questions. Let's thank Michelangelo.
Thanks.